Hello, everybody. Welcome to the IRA Robotics Virtual Conference. We're Mission Design and Automation, and we're going to do some presenting on some 3D printing and how we use that to better our company and make it more efficient for automation. Mission Design and Automation was founded in 2004. We're located in Holland, Michigan. We're around 50 employees, and we work in the automation field with robotics, vision, testing, gauging, welding, heat staking, sonic, and assembly, dispensing, and conveyor applications for our customers.
So we originally started our 3D printing branch here with a monoprice maker, Ultimate. It was very entry level. We were only able to have a single material extruder, and there's a very limited build space. After a few years of using that here in the facility, we realized the capabilities of 3D printing. We decided to upgrade into the Ultimaker S5 Pro. This allows us to do dual materials and PVA material, which is a support material that allows for more complex parts as well as printing in a larger print volume.
So some of the parts that we've come across, you can't really machine them. So this is actually good for 3D printing. It doesn't hold us to some of the design work that you have to do to make it machinable. In the 3D world, you can pretty much do whatever you want and get it printed. So the material that Aaron was talking about is PVA. So that is a support material that is used in the printing process that once the print's done, you put it in water and it dissolves away. So this allows you to make complex designs possible. So we got a little video here showing what our printer looks like in action, a little time-lapse video.
The white material surrounding the gray part is the PVA support material that we were talking about earlier that allows for the complex part. This part it's printing right now has multiple layers built within inside that a normal 3D printer or manufacturing process could not obtain by machining.
So this is showing that when you put it in water, how the material dissolves away, it gives you a final product. Some of the areas that we've found really beneficial for using 3D printing is clip drivers, nests, grippers, R&D, customer parts. We even did a lot of COVID-19 PPE materials, prototyping. So for an example, the grippers over here, customer parts in CAD are not always what they are in real life. So we like to get some of our customer parts and we'll actually make the clip driver. We'll 3D print that instead of using steel and machining it. It cuts down on the hours it takes to get an actual product made. So we can make sure that our designs work with the clips and our customers' parts. We also do that with customer part nesting to make sure that what we design will actually work in the real world. And you just save a ton of time and effort that way, so we can get that to our customers in front of their face faster. So this is another application. It's a bin pick. You can show the video. Instead of machining mounts to hold a gripper, machining gripper fingers, waiting for customers for their parts, a customer can come to us and say, this is our problem that we're having. We actually 3D printed the customer parts. We 3D printed the grippers that go on a shunt gripper. And then we also 3D printed the mount that holds the gripper. So instead of 24 hours of machine time in a normal CNC, we can get this down to 10 hours in printing, and we can have something the next day or two. And then we can set it up on our R&D cells and show the customer how it works, basically, with their part instead of just some generic part that we have here already. This is another proof of concept right here. We had a customer come to us and they wanted to fold cardboard in a certain direction. So we came up with a concept. We 3D printed this. And again, we didn't have to follow the laws of CNC. So we could make it whatever shape we wanted to. And this was a good demonstration to show our customers, hey, we can actually do what we say we're doing at a very low cost to us to get the details made. So proof of concept is very quick, it's cheap, and very easy to do for our customers.
So, and then a couple more options that we have is, like we said, we have those grippers that we 3D print. A lot of it's for our initial testing and R&D, so that we can prove out what it's going to work before we hold up time in time CNC. So the grippers for the R&D cell cost us $3 to make. It only cost 3 hours. It was only 3 hours to print it, whereas holding up our CNC department and having those made would be considerably longer and considerably more expensive. The same with the clip drivers, as shown. Those are only 28 cents for us to print each. And when our customer data is changing and not always working as we initially thought, then it's a lot quicker and a lot easier for us just to whip out a couple of these prints, and they really show our capabilities before our final process. We have our 3D printer S5 Pro. Allows us to print a ton of different materials, including PLA, tough PLA, nylon, CPE, and PVA.
So this is another application where we figured out doing some cost analysis. So we used to have an aluminum block with this turn-in T-nut and a screw to mount our polycarbonate guarding. And we decided that, hey, this is probably not the easiest way of doing it. So we developed this turn-in style block. So we started on our printers, and we started printing it on ours, and decided that it was probably better to go with an outsourced 3D printing. The finish is a little bit better for a production level part. So we actually produced these with a partner of ours, and the cost difference, our normal cost is $3 to $4, and this one's around $1 a piece. So there's quite a savings there. So our printers are good for R&D and prototyping, and then we work with our partner Forerunner, and he does more high-level production, high quantities, and the finish on his printers are a little bit better than ours. So we'll let him get into some of the stuff that he's capable with and show you some stuff that 3D printing is capable of.
Hello, everyone. My name is Paul DeWys. I'm the owner of Forerunner 3D Printing. We switch to the next slide. Oh, there we go. Oh, sorry. I didn't realize to back up a slide. Forerunner 3D Printing, we're located about 30 minutes north of Mission, up in the Coopersville area of Western Michigan. Started out 10 years ago as a machine design firm. So we did then and continue to do to this day contract design for overflow machine builders and stuff like that. And that led us to, in 2016, we kept running into this situation where our builders were, trying to go out to other 3D printing companies to get details printed. And the 3D printing companies just didn't understand machine build, didn't really understand the industry. And so we saw an opportunity to come in and say, okay, we design machines, we've done it for a long time. We could be the guys to really take and bring additive and 3D to the machine build industry, at a higher level. And so that's what we did in 2016. And since then, we've been kind of growing our capabilities and, growing relationships with companies like Mission. So I've got some examples here today. And the first one we're going to talk about is some nesting. So a lot of times when people are doing nesting, traditionally, they'd be machining it out of Delrin or maybe like HDPE, some kind of engineering plastics, maybe aluminum, things like that. And, one of the things that you run into is, the more complexity that you put into the nest, the more cost and time and difficulty that's going to create on the machining side of things. And so one of the big secrets to additive manufacturing, and if there's one thing you remember from this, it's the golden rule. Complexity is free. It's size that drives cost. So, for example, this nest right here, Customer needed to drive some clips into a plastic part, and they also wanted to integrate their sensing and everything like that into one detail. And so we're able to put in all the holes. We're able to actually print the taps in there, or the threads in there. And we're able to put a spot on the end to put a part mark. And so we're able to introduce all that complexity into a single piece. But compared to what it would cost to do this through traditional, either multiple setups on a 3-axis machine or getting it into a 4 or 5-axis type machine, we can be really, really competitive on cost. Where things kind of fall apart is if you have a really simple nest, something that doesn't have a lot of complexity, it's always going to be cheaper to do something like that in a 3-axis mill or at a Bridgeport. Complexity is where we can really, unlock things for machine builders. Another interesting thing that we started doing, so all the black components that you see, these are nylon 12. The gray that you're seeing here, this is actually TPU rubber. So a lot of times, in the past, if you've ever dealt with 3D printed rubber parts, they tend to be, not really something that will hold up over the long term. In the last 2 years, this new TPU material has come onto the market. And I mean, it's incredible. Not only is it, really end use and really robust, but it's also, it's Class A safe. So for this example here, we have a door handle nest, and this door handle has chrome on it. And so we can't obviously mar that in the nest. So what we did is we printed a black nylon retainer, essentially, and then we inserted it with TPU inlays. And so anywhere where the chrome comes into contact with the part, it's being in contact with TPU rubber, not with the nylon. So this is kind of a hybrid approach for nesting. And we find that we can displace cast urethane with this process. So, if in this case here, the customer actually ended up needing 8 of these nests. And so, they would have had to pour a bunch of cast urethane, and the lead time on that was in weeks. We were able to do 8 of these nests, and with the nylon 12 base and the TPU inner, I think we had these out the door in 1 week to the customer, because there's just so much more speed. For example, in the PowerPoint that you're looking at, you can see in the upper left-hand corner those 4 nests in a row. There's actually 40 of those, and each of those is a combination of nylon and TPU rubber. And again, we can pack a lot of parts into a single build. So, Mission's in-house capability is that FDM machine that you saw. We're running all of this on HP MJF machines, which is a nylon bed process. So we can lay parts out in the X and Y direction. We can also stack them in the Z. So that enables us to get hundreds of parts into a single build and drive that per part cost down. So yeah, there's some other nesting examples on that sheet there, the upper right-hand corner. That's actually a bunch of nesting we did for a mission, a piece of equipment for mission. How many pallets worth of those did we do?
There was like 25.
Yeah, so about 25 pallets. Each pallet has all the nesting you see on there. And I think we got it done in 3 full builds on the MJF. So within the space of about probably 6 or 7 working days, we're able to turn all that nesting around and get it back to these guys for integration into their machine. And, some of that was pretty, there were some deep pockets where we needed square corners down at the bottom, or, some tapers, things that would have been very difficult, if not impossible to machine. But with printing, it was pretty simple. These guys designed in what they needed, and we printed it, and it worked.
Yep. Yeah, there's a lot of 3D surfacing on some of them that, in a mill it would take a long time to do, but in 3D printing world, it's really quick.
Yeah. All right. So next up, we're going to take a look at some end of arm applications. So same basic rule applies. Complexity is free. It's size that costs you. So we've got everything ranging from some really simple gripper fingers here. The difference is there's actually a bunch of knurling on the inside of these fingers that would have been extremely difficult to do with any other manufacturing process. But here you can literally go in and design whatever knurling or grip pattern you want directly into kind of the fingertip pads, and it prints right into the part. So, gripper fingers like this, if you needed one set of these, we're probably in like the, $150 to $200 range. If you needed 15 or 20 sets of these, we could be all the way down into like 25, 30 bucks a set. Because again, as we fill our machine up, the cost per part comes down because we're spreading the cost out across all those parts. Another example, so this is getting more, more complicated. So we have a pair of, or a set of gripper fingers here. Again, we've got the black part is the solid nylon. And then the gray tips, those are actually TPU rubber. Again, you could pick a chrome part, you could pick a painted part, you could do a lens, anything that you're worried about marring or scratching, these fingertips won't cause that issue. But again, we're able to print a really aggressive pattern into these TPU rubber parts. And another really cool thing about this, we actually have the airlines printed into the part itself. So there's, it's hard to see on the camera, obviously, but there are suction cups inside of each one of these TPU rubber fingertips. And then the airline or the vacuum line actually comes out down here with a fitting. So we're actually routing that vacuum path through the inside of the gripper finger. And this would be in a situation where like maybe you're trying to reach into a really tight area, or maybe you're worried about getting vacuum lines hung up on something with a robot moving through space. You print all that right in, get your lines back out of the way so you don't have to worry about catching them on something or, trying to get into a tight fit to grab something. And another interesting thing about this nylon is it's about half the weight of aluminum. So if you're dealing in cobots where, you're extremely load limited because of their cage-free abilities, this material can get you a really large end of arm tool on a really load limited cobot and still leave you enough capacity to be able to pick parts and actually do something with it. Or if you're running a big industrial robot, and again, you're trying to really throw that robot around and you can't afford to have a bunch of weight out there, again, you can print it in nylon and literally cut your weight in half. And we've done a ton of wear testing and strength testing. Obviously, it's not as strong as nylon, but for pretty much every application we've come into, we haven't found a situation where we couldn't get this to work versus an aluminum detail. This is another good example right here. Again, of complex air routing. So we have 3 vacuum cups in this area, and that all comes off of one fitting. And then we actually have a compressed air blow off coming through the other area, and that's off another fitting. So essentially, plug in a vacuum line, plug in your compressed air line, and you're done. All the manifold work is done inside the part, and it's not all gun drilled to pieces. There's no clean outs or anything. It's just port there, and then each of the ports that you need for your various vacuum and compressed air. And then this guy is kind of deceiving, but it's one of my favorite examples of complexity. So you've got an array of suction cups on there, and obviously they're at a tip in this direction, but they're also tipped in this direction as well, which turns this into a compound angle part. So really the only way to effectively do this would be on a 5-axis machine. And so, you can imagine trying to, cost justify putting something like this on a 5-axis versus, we ended up doing 4 of these, lay them into a bed, run them all at the same time. And that little bit of tip in both directions doesn't matter. It's not going to add a bunch of cost. You're just paying for, however tall that build ends up being. And then lastly, one of the things, I'll take that too. One of the things that we're kind of coming down the pipe in R&D is actually taking our TPU rubber, which again is extremely soft when you design it with a thin wall, and actually printing TPU suction cups. It's pretty hard to see in the video. If I can get a little bit closer. Those suction cups are actually not round. They're actually contoured. So these 2 are contoured suction cups. That one right there actually has a half moon taken out of one side of it. And so, one of the R&D projects is trying to figure out, we've printed regular suction cups that can allow you to pick up and drop a steel ball 100,000 times, no problem. Next phase of R&D is going to be showing that suction cups with these custom profiles will hold up to hundreds of thousands of cycles in a shop environment. But we're really excited about this TPU because, I don't know about you guys, but when we design machines, it always seems like we use double the amount of suction cups we really want to use because you never have a nice, perfect flat
Yep.
face to pick parts on. You've always got a weird cutout, or you're working around a bunch of stuff. So you wind up with all these excess suction cups. And, you know, we really think additive could unlock the ability to be able to do one-off suction cups that would never be justifiable in cost to do any other way. But with this would be no big deal.
Right. And the replacement cost too, right? If
Yep.
something breaks, it's call up
3
Paul
days.
and he gets them made. So
Yep, 3 days later, and we got a replacement
yep,
out.
it's not a custom thing anymore, really.
Exactly. So yeah, so that kind of takes me through kind of, you know, the next step in additive. These guys talked about the prototype and tryout. We're kind of more of the production, larger volume, maybe more end use in certain applications. And that's kind of the natural workflow that we've kind of developed, you know, Mission working with Forerunner over the last, you know, year or so.
Yep.
So yeah, so I guess is there, open it up to questions at this point? Okay, I think we're getting.
I think we're done.
I think we're done.
I think we're done. We're getting the done sign. So thank you guys. Have a good day.
Thank you.